Okay, I'm Jim McLaughlin. This is Occupational Ergonomics and Safety. This lecture is on heat stress, and we're going to talk about a few of the concepts related to metabolic energy expenditure as it relates to heat stress. Please read Chapter 28 in Occupational Ergonomics Theory and Applications, second edition, edited by Drs. Bhattacharya and McLaughlin. To start out with, it's a cross-section of the head where we're showing you the location of the hypothalamus. This can be reached also through the roof of the mouth with a two-penny nail about 2 inches back going straight up into the brain. It's important to understand the hypothalamus is very much like the thermostat of the body in terms of controlling the autonomic nervous system, and it's responsible for temperature regulation in your body. So very much like a thermostat is in the room that controls the temperature to make you comfortable, warm or cool, the hypothalamus serves very much the same function in terms of core temperature. This is a rather complex diagram of the various aspects of heat outcomes. You start out by reading this in the center, where we look at heat loss by radiation and convection. It's less than that of metabolism, meaning that you're working and activating the muscles and causing them to warm up, and so the temperature rises, and as it rises in the body you begin to sweat. You also have vasodilation and to release the heat from the core through the skin. And if you continue to work, there are 4 outcomes as a result of heat exposure. First, if you follow this aspect of sweating, the first is prickly heat that you have here. This is for people who work in chemical environments, for example, where they're exposed to hazardous chemicals and gases, vapors and fumes and so on. And if they're say working in the petrochemical industry, for example, and they have to have Tyvek suits on, that they begin to sweat underneath these suits. They don't have evaporative cooling because they're impermeable or semi-permeable. That what happens is that the sweat glands become clogged. As a result of that, you begin to feel itchy, and these are the sweat glands not allowing the moisture to escape freely, and it gets classified as prickly heat. Another outcome is heat cramps. This is a drain on body salt to the body, and it usually occurs in larger muscle groups. Many of you have probably experienced this if you've gone out and exercised quite heavily, and then your legs will start to cramp up, or your upper body, but it tends to focus more on the larger muscle groups. 2 other outcomes from this, and so if you're trying to shed heat through vasodilation, you have fatigue of the sweat glands after a period of time. You diminish your sweating. You have a rise in body temperature. Then you have a failure of the central control mechanism, which is your hypothalamus, and this can lead to heat stroke. This can, in severe situations, you can have brain damage. Why? Because you're basically heating that core temperature to the point in which you're denaturing the protein in the body, and it can result in fatalities as well. So this is a rapid rise. Notice that these mechanisms all come down as a result of heat exposure, but what happens is that the hypothalamus is out of control in terms of being able to cool down the core temperature, and you have this rapid rise and leading to heat stroke. One other outcome is heat exhaustion, and notice it follows the same pathway as leads to heat stroke, but there's a major difference right here that you need to know, and that is that you have augmented skin circulation and sweating, and all of that leads to circulatory shock. Basically, the body shuts down on you because of the fact that your water level is very low, the electrolytes are low, the heart is having to pump very hard because it has inadequate blood flow to back to the heart area, and you basically are incapable of performing anymore because the body is shut down. and you cannot function anymore. You're not. Most of it is not only a physiological issue but also a cognitive problem. Notice that there's a difference here. You do not have to have heat exhaustion to lead to heat stroke. Again, the heat stroke is related to the failure of the hypothalamus to regulate the core temperature, whereas heat exhaustion, the body is working as it should, and it's just reached a point of exhaustion in terms of fluid levels, elevated heart rate, and so on. The heat balance equation is four thermodynamic processes. You have metabolism, evaporation, radiation, and convection. If you're dealing with cold stress, you also have conduction, and most of the issues with conduction are in the maritime industry, where you're surrounded by water. If you fall in the water, for example, and it's very cold water, it will sap the heat from your body, and you become delusional, disoriented, and so on. And a lot of people drown just because of that, rather than the fact that they, a swimming issue. Many can swim, but once you quickly lose that heat from the body, it can result in drowning and fatalities from the cold exposure. Related to heat exposure, however, though, the focus is evaporation, radiation, convection. Metabolism information you can get from tables, or you can calculate it on an individual level if you have the right instruments, such as heart rate monitoring, oxygen consumption, and so on. Evaporation and metabolism, if you looked at them mathematically as expressions, metabolism is a plus, or heat gain. This is a physical activity of the worker determined by the job, or is paced by the worker. Heat loss in evaporation, that would be a minus as a mathematical expression. That's the relative humidity and air velocity across the skin. Radiation and convection are plus and minuses as symbols. You gain it or you lose it, radiation, with the temperature differential between the skin and the surrounding objects. The same thing as for convection, however, in terms of plusing, gaining or losing, but the key difference here is that the differential between the skin and the ambient air. So it's very important to distinguish radiation gain or lost and convection gain or lost by the mechanisms in which heat occurs. So in the case of radiation, we're looking at the differential between the skin and the radiation coming from that particular object. And this could be a blast furnace, or it could be the sun, it could be any radiant source coming in. Here, in convection, you're really looking at the difference between the temperature of the air and the skin. So the air is the mode in which the body is being heated up. The reason it's gained or lost is that we are radiating surfaces, so we can lose radiation because of the heat from our body. That's from the vasodilation that we talked about a little bit earlier. Convection would be the same way in terms of the skin temperature being warmer than the air, but it also can go the other way, and that is the air is warmer than the skin, and for convection, and the radiant load, for example, the sun, can be greater than what the radiant load would be for the human body. So understand and distinguish between those two, but that's why you can have a plus or a minus with radiation convection, and you can only have a loss with evaporation. You can only have a gain or a plus with metabolism. If you ever have a zero with metabolism, then that means the body has ceased to function and you've expired. Heat symptoms. Heat cramps, these are painful spasms of the muscles. All of you probably experienced this sometime in your life. The heat rash, this is prickly heat, as I talked about a little bit earlier. This is just the red vesicles, or the pores of the skin continuously wet with unevaporated sweat, and usually this occurs because of people wearing protective clothing. Heat exhaustion, the skin is clammy and moist, and you have symptoms of fatigue, nausea, headache, and giddiness. Heat stroke, the skin is hot and dry with an elevated rectal temperature above 104 degrees Fahrenheit or 40.5 degrees Celsius. It's important to distinguish between heat exhaustion and heat stroke, especially where the skin is clammy and moist in heat exhaustion, and hot and dry with stroke. Hot, as I mentioned, because of the failure of the hypothalamus, this is a very important symptom right here to recognize, because the person may suffer brain damage and may die as a result of the heat stroke. You want to get them out of the sun or away from the heat source as soon as possible. get something cool on them. For example, soak a shirt or any piece of clothing and water and put it over their core, and of course calling 911 to get the right people there to help them recover as soon as possible. So this is a very big deal, and if you ever come across it, looking at someone, if the skin is clammy and moist, obviously you want to get them cooled down too. You'll recognize some of the symptoms as I've mentioned here, but more important is if you see someone with hot, dry skin and they've fallen over and they have issues in terms of heat exposure, this obviously is an emergency condition which you need to take care of. Heat balance equation. We're just going to have you focus on MERCS right here, MERCS. Usually the body heat content changes in that is usually kept the same in terms of some of the mathematical expressions. So we just focus on metabolism, evaporation, radiation, and convection. To solve this equation, you need to have a table or be able to collect these measurements from the individual in terms of metabolism. You can get from instruments air temperature, water vapor pressure, wind velocity, and mean radiant temperature. Convection is a function of the temperature difference between the ambient air and wetted skin, as I mentioned before. Usually the standard that's looked at there is temperature of the skin at 35 degrees C. Radiant function, this is the fourth power of the absolute temperature for surrounding objects, and this kind of got wiped out a little bit, but put that fourth power right there between the radiant temperature, T sub W, minus T sub Sk, which is the temperature of the skin, to give you those values. And then finally evaporation. This is a function of air motion and water vapor pressure. The water vapor pressure here is standard is 42 millimeters of mercury. This is at the skin at 35 degrees C. And as you see up here, this pretty much holds as your standard. That converts to 95 degrees Fahrenheit, by the way. So indices of heat stress, there are four: effective temperature, predicted 4-hour sweat rate, heat stress index, and wet bulb globe temperature. The effective temperature, there are modifiers here: corrected effective temperature and effective temperature prime. Don't be concerned about that. You can look them up in tables that make correction factors. This is mostly used for indoor air quality kinds of surveys. If the air is too dry, static discharge or dry eyes, things of that nature. Or if it's too high, then you have mold issues. But this is really looking at a wet bulb and dry bulb and airspeed. So it's really between the two. You can get relative humidity. Airspeed, it can either be driven by a powered fan, or you can just have the natural flow go by. But in most instances, it's by a steady flow of air going through to get the evaporative loss of moisture. Predicted 4-hour sweat rate tends to be used more in the military. This is how many liters of sweat you would lose in a 4-hour period. Again, we're looking at a wet bulb and a dry bulb. In this case, we're also adding the globe. And the globe temperature is looking at the radiant load as well. And the globe is to simulate what the body is. Heat stress index, this is evaporation required to give you the metabolism, radiation, and convection. The index itself is the sum of it is 100 times the evaporation required versus divided by the maximum evaporative capacity in the environment. So multiplying this product, is anything over 100 is a heat gain, anything under 100 is a heat loss. Most of you will see the wet bulb globe temperature if you're measuring things in the environment. Notice there are two equations at the bottom. One says for a solar load, the other one is without. Don't be fooled by that. The issue with the solar load is that anything with a radiant load should use this top equation right here, 0.7, which is a constant, times a natural wet bulb. A natural wet bulb means you don't have a steady flow of air coming across. It's just the natural air currents that flow by this wet bulb. The next is the globe temperature, which is the black body that represents the body's picking up radiative load, and then 0.1 is your dry bulb. This is just like a regular temperature sensor. Indoors, natural wet bulb, notice they have 0.3 times the globe temperature. If you don't have a radiant load, then the globe temperature is not going to be different than a dry bulb. But if it is a radiant load, then that globe temperature is going to heat up a little bit and show that difference. So this kind of, when you see this equation like this, it hedges your bets a little bit. They're saying that, I don't see a radiated load, but there might be. In that case, then it's going to give you a truer value. So I like students to memorize this in terms of Fahrenheit and Celsius. Right here, a rule of thumb is that if you're trying to convert to Fahrenheit, take that temperature in Celsius and double it and then add 32, and that gives you a number that's fairly close to Fahrenheit. It's a good rule of thumb if you're looking at temperatures between, let's say, 60 and 80 Fahrenheit. But beyond these ranges, that rule of thumb doesn't hold up as well. But it's not bad for giving you at least an estimate of, if someone says, well, it's 18 degrees Celsius outside. Well, what does that mean? So you can quickly do the math to figure out what that is close to Fahrenheit. So I asked this question here: what's 38 degrees C in Fahrenheit, and what's 95 degrees Fahrenheit in centigrade or Celsius? And the answer is, if you do the math up here using this formula, this is 100.4 degrees Fahrenheit, and this one here is 38 degrees Celsius, and this represents the upper and lower limits of the core temperature in which the body functions in an optimal manner. So if you go beyond 100.4 or 38 degrees C, you have heat stress issues that will compromise your performance. If you go below that, 35 degrees C or 95 Fahrenheit for core temperature, the body is also compromised in terms of performance, cognitive functions, physical functions, and so on. So know those ranges. This is a neck-time nomograph. We have a couple things going on here. On this vertical line, we have the dry bulb temperature. On this vertical line, we have the wet bulb temperature. In between, this neck-time nomograph actually shows what velocity of air does in terms of impacting the overall temperature that you might be experiencing. So as you would know, the higher the air velocity, the higher a fan speed, for example, going across your skin, the cooler you're going to feel if that temperature is below your core temperature, your body temperature, 98.6, but the temperature of the skin, we're looking at about 35 degrees C or 95 degrees Fahrenheit. So for example, if we look at this line right here, where we just took some measurements of the air, that says 80 degrees Fahrenheit, and it comes down to 65 degrees for wet bulb right here. Let's say if we had just a fan temperature, let's say take it up to 400 feet per minute, and we were to follow that line straight up right here. Let's try it again. It intersects right there, and then the idea is to take that where that intersection is, and then drop that line straight down to here, and the value that you pick up looks like it's about 64 degrees Fahrenheit. And so even though you might be looking at 80 degrees as a dry bulb temperature and 65 as a wet bulb, because of a fan speed coming across at 400 feet per minute, then it's going to make it feel like 64 degrees Fahrenheit. That's because of the evaporative cooling across the skin. Time limited compensation, zone A, zone B, and zone C that you see right up here. This full compensation means that you can work in a steady state without having to take any breaks. Zone B means you have to take breaks right here in terms of work-rest regimen. Zone C shows that you completely have exhausted your resources, and you start to have sweat rate failure and fatigue and so on, which compromises your performance. So you can see the sweat rate is linear. You can see the temperature of the skin is linear on this graph. But notice that the core temperature and the heart rate, the inflection points are right where this time-limited compensation occurs, meaning that your core temperature is starting to rise, and you really need to take some time out. You have to have a break in order for that core temperature to come back down and be horizontal again. The same thing for the heart rate. The idea is that you can increase it, but over time, if you are working to a period of exhaustion, that heart rate isn't coming back down to baseline levels and can cause problems for you. So the idea is that the higher the effective temperature, this is your wet bulb and your dry bulb, the greater the heat stress issues that can occur. So if we were to give you a table as an example of energy cost and task analysis, this shows you what kilocalories are per minute, sitting, standing, walking, and so on. And here's your ranges from hand work all the way up to whole body work. And notice your basal metabolism is always going to be included in here, and in this case for a standard individual it's 1 kilocalorie per minute. And so if I would give you an example problem down here saying that, okay, we're doing work with heavy tools, so we're standing at 0.6 kilocalories per minute. That's where this came from right here. We have 2-arm work, 3.5 kilocalories. So they're looking at this and they're saying, well, with the heavy work that's being done, we're going to take that out of range at 3.5. We add in a basal metabolism, that's 5.1 kilocalories per minute. Now notice that this is for a standard individual. You read the small print right here, 154 pounds. So you look at that and you say, okay, I want to find out how many kilocalories per hour, so you multiply that times 60. That gives you 306 kilocalories per hour. But then the question comes up, you say, well, does this apply to everybody? And as you know from energy expenditure, that the larger the mass of a particular individual, the greater the energy expenditure because of the movement of that mass, even though the person may be doing exactly the same job. So if I were to ask you, give me the same calculations for someone who weighs 250 pounds versus someone who weighs 154 pounds, you should know that there's going to be a different metabolic expenditure for the 250-pound individual versus the one who's 154 pounds. Well, so let's see how this works. So if we go to this chart right here, and arbitrarily I took this temperature line at about 27.5 degrees Celsius and about 82.5 degrees Fahrenheit. I just drew that line across right there. I just randomly grabbed it because I wanted to show what this looked like on this chart. Anything below this solid line, it says I can work continuously. So this is like my zone A that I mentioned earlier. If I go between that zone and the next one, you see the dotted line right there, right here, that now we're talking about 75% work, 25% rest. So in the case of the 1 hour of continuous work, that equates to 45 minutes of work and 15 minutes of rest. And you can see the rest of the legend as it pans out right here. 50% work is 30 minutes on, 30 minutes off. 25% work is 15 minutes on, 45 minutes off. So the further up you go in this, either by temperature or by work, then as the way you see these sloping lines, it changes how much time a person can work on and off in terms of that zone A versus zone B work compensation and rest period. So we calculated the individual weighed 154 pounds, and what we can see right here is that if we draw that intersection right where the two lines come together to bring us down, that's 306 kilocalories per hour, that the person has already broken that working continuously, and it says that that person can now, between these two lines, work for 45 minutes with 15 minutes off. However, if you do the calculations for the individual who weighs 250 pounds, and the way you do that is you take that 154 pounds, divide that into 250 pounds, that gives you a ratio of about 1.5 as a multiplier to the 306 kilocalories is what we determined based on the 5.1 kilocalories per minute right here times 60. That gave me my 306. So I go 1.5, which is my ratio between 250 divided by 154 times 306, which then gives me my new value. It's about 496 kilocalories per hour. So we're going to draw that in for that 250-pound individual, and right where it intersects, right here between the temperature and line, notice that we've gone up into, really almost two different zones right here, really right on the bubble. But we can say, conservatively speaking, that maybe we want to be, just be careful with in terms of heat stress, which means that now they're between these two lines, which means that we're working for 15 minutes, 25% work, and we're giving a rest of 45 minutes. Now, initially you're going to think, well, I want to get this, skinnier person right here, or the person who weighs less, 154 pounds, to do this work because I can have them work longer, at least 45 minutes versus only 15 minutes. But again, I'm trying to illustrate to you when it comes to heat stress, and energy expenditure, there are differences in weight and mass. And I can tell you, for example, when I've done my triathlons, I always tend to struggle a lot more because, as you know, I'm a bigger person, about the 250-pound range, that suffers a lot more when I have radiant load and high temperatures, and that's because of the mass issue that I'm dealing with, as opposed to someone who would weigh a lot less and be able to perform more optimally in that kind of in those kind of conditions. So to end, we have a checklist for controlling stress and strain. Lots of things in terms of reducing physical demands for high-powered work, rotation, and so on can come into play. Radiative load and a line-of-sight barrier. It's important to keep these barriers clean so that they can reflect the radiant load. They can be compromised by up to 30% if you don't keep them clean. Convective load, as I mentioned earlier, we're looking at the air temperature. If it's above that skin temperature that I mentioned to you, that 35 degrees C, right here, you want to reduce the air temperature, and it seems counterintuitive, but you don't want to increase the airspeed. Why? Because basically that air going across your body is warmer than the skin, which means it's going to be heating you up. You can have fans on, of course, if you have temperatures that are less than the skin temperature here of 35 C or 95 Fahrenheit. The fans work just fine. In most conditions it does work, but most people say, put a fan on me on the really, really hot days. That can be a problem. Cooling, you can decrease humidity if you have indoor environments where you can control that, or airspeed, or increasing airspeed across the skin. And you have high fan movements, which makes a difference. You can also decrease the amount of clothing being worn. Work practices, shorten the duration of exposure, and so on. Exposure limits, limit these exposures. Formal indoctrination, educating workers about hydrating properly, and so on. And then also, let's say you're doing construction work, recovery of an air-conditioned unit nearby, a trailer of some sort, does make a difference in terms of quicker recovery. And finally, personal protective equipment, air-cooled suits, excuse me, are very helpful, as well as making sure that the people who are going to be working in hot environments have medical evaluations, and you can control for the age, and control for the gender, you can control for the weight, any medications they might be using, and so on and so forth. And then, of course, always at the end, any heat waves that come out, making sure that there's proper hydration available, and so on, and that the amount of exposure is limited. That ends my lecture on heat stress. I thank you for your time and attention.